In this presentation, we're going to initially have a look at destructors and then tie everything together into an example that shows you all of the different ways of constructing a class alongside a way of destructing the class. But start off first of all with the notion of destructors. Destructors, they're quite simply a way of enabling us as programmers to have control over how an object gets to be freed up, to be destructed. You can see the general form of how it's used here on the screen. So if we have a class named foo and we precede it with the ampersand in terms of, if you like, the method signature, is then signified as a destructor. Doesn't take in any parameters, doesn't return any data. So it's actually something that is called automatically for us. So whenever we are freeing up objects, be it from the stack or the heap, or wherever we have them stored, the destructor will automatically be called on our behalf. And it's the job of the destructor to say, okay, if we're going to delete this object, to free it up from memory, how do we go about doing that to do it safely? Primarily, we will use it if we are allocating some memory, linked memory within that object. And we want to have an opportunity in deleting the object also to delete the thing that we're linked to. So that's most of the occasions where we have need for a destructor. It'll be for that purpose. Doesn't only have to be that. If you have an object that establishes a network connection, opens that, or takes out a lock on a file or some database tables or whatever, you may want to put a check in the destructor just to make sure that these the connection's been cleaned, the lock's been released, those types of things. So it gives us an opportunity to take actions to safely ensure that whenever that object disappears, we're not going to have anything left lying around or left open. Wouldn't be C++ unless there was a few sort of gotchas in terms of things to be careful about if we're using destructors. So we're going to have a brief look at just a couple of them here. And we'll start off with a piece of code. So we'll have a look at the class foo over on the left-hand side. In the public section, we have a pointer to an array of data, integer data. We'll have a constructor in line 5. This is a parameterized constructor, takes in the size, and will initialize data to point to an array allocated somewhere in the heap of that specified number of integers. Line 6, we're declaring a destructor. And we say that whenever that object is destroyed, then we will delete, and we're using the right form here for deleting the array of data that the data variable itself points to. We've got a fragment of code underneath this that is going to be slightly problematic. It's called test. Line 3, we declare a new foo class, parameter size 10. So that will create an array of 10 integers somewhere in the heap. In line 4, we're creating another instance called b. And here we're using the copy constructor. So we get one by default, we don't have to define it. And the default copy constructor uses pairwise assignment. So it will copy all of the member variables from foo from the A instance across into the B instance. In line 5, we're setting array element 0 in A equal to 12. And in line 6, we're printing out array element 0 from B. And that will also give us 12 because effectively pairwise comparison means that they're sharing data. And at line 7, it'll crash. So we'll have a look at why we have these behaviors. So look at the diagram over on the right hand side. After we've, on line 4, after we've run the default copy constructor, it will ensure, or the outcome of it, is that the data pointer from both A and B will point to the same region in memory. So that array of 10 integers that was initially created whenever we were creating A. And that means then that if we're accessing it either through A or B, we'll be following it through the same pointer, accessing the same bit of memory. So making changes to one will change the value that we access through the other. And we probably don't want that. The issue in this is that whenever we get down to the end of the block in line 7, A and B are instance variables. They've been created somewhere on the stack. They're going to be freed up. Because we have defined a destructor, that will get to be called. Now let's assume that A initially is the instance that is deleted. when we are removing that, then it will result in the memory that was stored in the stack being freed. So we'll have A's memory being released. It'll be fine, it'll work perfectly okay. And then whenever we get on to freeing up object B, its destructor will also be called, and its pointer will point to the same chunk of memory. But effectively then we're going to try to free up memory that previously was marked as having an integer array. That'll be fine. That's now previously been marked as being free and empty. And that won't work. That'll result in the program crashing. So that's a problem with this particular one. If we also have a look at copy assignment, we actually have a slightly worse problem. So again, foo classes over on the left-hand side, exactly the same class as defined in the previous slide, hasn't changed. The test at the bottom is now slightly different. So in line 3, we're declaring A and B, two separate instance variables, both of size 10. In line 4, we're using copy assignment. So whatever B is being set to the same value that A has. And we have a default copy assignment constructor built in, and again it will do a memory pairwise comparison. So we'll copy across all the instance variables, in this case data, from A into B. In line 5 and 6, same as before, we're accessing array element 0 through A, and we're printing out array element 0 through B, and we'll get the same answer because they're going to share the same data. And at line 7, we'll crash, as we always did. Now, why is this slightly worse? You can see over on the right-hand side. So whenever we create in line 3, our stack and our heap will look as is shown there on top of the slide. So two separate instances on the stack with separate pointers at this point in time, pointing to two separate regions of allocated memory on the heap. In line 4, whenever we run the default copy constructor, we will end up then with both pointers pointing to the same chunk of memory. It will result in orphaned memory, so we've lost that particular integer array, can never get it back. It's slightly a moot point because in line 7 the program will crash, but ever so slightly worse. So we need to be careful about using these things and about any time we're copying or assigning objects when they point to or refer to other data. There's a simple rule that will help us navigate through this. It's known as the rule of 3. It says here, if a class defines one of these where we have a destructor, a copy constructor, or a copy assignment operator, if you define any one of those, it is very probable you should probably define all of them. So all of these 3 things really go together in a package. So if you find yourself thinking, oh, I better put it in the destructor to free this up, you automatically then should be thinking, I probably need to put in a copy assignment constructor and a copy constructor as well. Doing that will tie the things together because the reasons you need one often apply to these other 2 as well. But we're bringing all of this together into an example. We'll do that now. So we're going to have some class, that's what it's called, and inside this we're going to declare all of the different types of constructors that we have. So we've got a default constructor, a copy constructor, a move constructor, a copy assignment, constructor operator overload, a parameterized constructor, and a destructor. 2 private member properties down at the bottom, same thing as before, we'll have a pointer to an array of ints, and we'll record the size of it. So again, this class is really just illustrating the different ways of constructing and destructing a very simple class. For the default constructor, you can see this at the top. Now the default constructor, also known as a no argument constructor, this is a default constructor because whilst it does have a parameter, it has a default value. So I can call this with no arguments. So I just call some class on its own, it'll be passed in there and given a default value of 10. Line 3, we're using the member assignment, setting m size to be size and creating a pointer m data to point to a new array somewhere on the heap of whatever size we have passed in. The parameterized constructor we see underneath this. In this case we're passing in an array of data and integer size, and again we allocate the size and we create a new array. So we're assuming here we don't want to tech that array, we want to duplicate the data that we're pointing to, and line 5, use the built-in copy through the standard template library to transfer data from one array to the other. For the copy constructor, we can see this here. We pass in a constant reference to another class. We are looking at the other size and setting it to do this, and we're looking at the other, creating a new array of data equal to the other size, and then again line 5 using our copy operation to do so. For the move constructor, so again the two ampersands, in this case here in line 3 all the magic happens. We basically tech the move property and tech the pointer to the data. Importantly, in line 5 we break the link in the other object, so we set its mdata equal to null. Very important to do that. If we don't, then we've got a chance that if we were to call our destructor, we would end up trying to delete memory that another object's taken hold of. The copy assignment operator, you can see it here. So if we've been set equal to some other constant reference, then in this case, because we exist, we are deleting our current data and we are recreating a new array to hold the new data. Now, if you think there's a high probability that the other class's array would be of a similar size to this one, you could put in a check first of all to see if the two sizes are the same, and if they are, then not delete it, just simply to do the copy. But here we're just assuming that it can be any old size. Line 7, we do the copy. Line 8, we're returning a pointer to ourselves. As a reminder, we did this so we can permit multiple chaining. A is equal to B is equal to C all in one line. Destructor then down at the bottom where we're deleting the array. We also could put in here, should put in here a test to make sure that the mdata is not null. In other words, we do actually point to something, so if it isn't null, then we should delete it, and that will do it safely. So key takeaways and all, you most certainly should adhere to the rule of 3. It's quite important. And destructors and the whole notion of copy assignment and all of those different types of operators, they're important, they're necessary when you get into objects that can be linked to other pieces of data or to other objects, or that can open up connections and things like that. It gives us a chance to safely shut down objects.